Alrighty, guys, can you hear me? Can you guys hear me? So, are there any questions before we get started? Any questions before we get started? Okay, then let's get started. We have a small class here again today, so if and when you have anything that's not clear, just interrupt. Your exams from last week, I graded them. The grades are up, and you'll get them back on Wednesday. The topic that we're talking about is continuity. So we're talking about continuity of functions. So what we're doing here is Abbott. We're in his chapter 4. So today we're going to cover chapter 4.3, and it's all about continuity. So so a function. So we take a set. Say inside D, as usual, Abbott, he always wants D to be 1. Then we're saying that if going from A to R is continuous, if it's continuous at some point in its domain, A is the domain, R is the codomain, it's continuous at a point if for any epsilon, you can find a delta such that when I keep x close to the point that I'm interested in, so keeping them close, you keep it within delta neighborhood, that implies that the function values be also close. And one thing to look out for, and this is the definition. One thing to look out for here is this delta here. But that delta here, this could depend on the constant C. So that's what it means to be continuous at a point, right? And we say if it's continuous, if f is continuous at all points in this domain. So let's this thing here, this is a bit tricky because we're going to be looking at another concept just maybe next time where you don't have this property. So here we're talking about continuity. So with any epsilon, you can find this delta such that when I keep the values close in the domain, you are guaranteed that the values over in the codomain in the image, they're also going to be closed. And this little observation here, this turns out to be quite important later on in the course. So let me just give an example to highlight this property here. So this here is an example in Abbott. Yes, Abbott's example 443. And it's a function that you've all seen many, many times. So you take the square function. Do nothing else, you just square. Then this function here, f is continuous. Countable, continuous. F is continuous at all points, which is of course not a surprise because it's a square function after all. And how would one go about proving it? Well, we need to compute. We need to control the function values, right? So we need to compute. We need to control the squares. So if I look at the difference over in the image, right, this is what I want to make small, and I need to make this small by keeping x and c close to each other. But I can write this here as, of course, by definition, this is the absolute value of x squared minus c squared. I can express this as x minus c times x plus c. So what we want is to use the definition up here, right? Give me an epsilon, I'll be able to find a delta, right? This could depend upon c. It could depend on epsilon. It can depend on everything that comes to the left of the statement. So it could depend on these two quantities. So what is it that I need? So given an epsilon, we need to create, we need to construct a delta such that what? Such that the values in the domain being close together implies that the function values are close together. So this implies that x minus c times x plus c, this is less than epsilon. Right? Any epsilon, we have to find, so give me any c and give me any epsilon, we have to create a delta such that this implication is true. And so that's what the hard work is. Can we find such a delta? And so let me try one. I have a recipe here. It's the minimum of 1. Then it's epsilon divided by 2 absolute value of c plus 1. Right, and here you can really see it, right? This delta that we're working with, the one we're going to try out, and of course this one here is ultimately going to work, but when we ask to prove something is continuous, we will have to create this delta ourselves. And you can see there's an epsilon here and there's a c here. In particular, these two things, they are in effect for this example here. So let's try it out, see if it works. Right, so now the assumption is that I'm keeping x and c close. I want to prove that this product over here and on the right-hand side, that this is smaller than this epsilon, right? And epsilon is anything that's positive. Let me try to do it. So I'll do x minus c times x plus c. Right, the first one was given to be smaller than delta, right? So we can put a delta here. That was the first one, and then I can use the triangling inequality on the other one. I get x plus c. So here I use this property, and I use the triangling inequality, right? So the absolute value of a sum is bounded by the sum of the absolute values. And then in the next step, I do nothing else. This is a step that we have done a lot of times before. Add and subtract the same thing inside. It won't change anything. And then what? Well, now I can use the triangle inequality again. I can use the triangle inequality again. Here I can put a delta. I can put x minus c, and then I get 2c. Now the first one, this is again bounded by delta, and delta is smaller than 1. So I can put a 1 there. Right, this is because x minus c, this is bounded by delta, and delta is bounded by 1. And now I'm good because I also know that delta is bigger than or equal to this epsilon divided by 2 absolute values c plus 1, and this is what I have here. So all in all, this here is less than epsilon. Any questions on the calculation we did here? Why is delta less than 1? Well, look at the definition. Delta is equal to the min of 1 and this epsilon. Right? So this here implies in particular that delta is less than 1 and delta is less than epsilon over 2 absolute value c plus 1. Because it's the minimum of the two. Okay, does it make sense, Priya? Why did you choose 1 for the definition? Okay, so we're not claiming anything here about uniqueness. We're not saying that this is the only way to do it. It doesn't have there's no exclamation point here. We don't have, there's no statement about uniqueness at all. If you want it, you could have put in a different constant here. So if I'm understanding you correctly, you said, why not put 2 here? Okay, so put 2 here, or put 1 over 2, or put a half here. Then you just have to create this constant over here would have to be a little bit different. Right, so there's no claim here about uniqueness of delta, right? It just says, give me an epsilon, then my job is to find at least 1 delta. Yeah, other questions? So I want to stress this again. So our delta depends on C. So if, and this is a big one, if you can find a delta that does not depend on C, well then we say F is, and this is a new buzzword, uniformly so that's a new buzzword here. This is this word uniformly continuous. So our example doesn't show anything about that. The only delta that we have created depended upon Z. And so we are not able, based upon what we've seen above, we are not able to conclude anything about uniform continuity. So this is just a this is just a note. So for f of x being the square function, you cannot find. So while Priya is right that you can choose many different deltas, so here you cannot find a delta which is independent. of C. But that's just, we're not doing that yet, but it's coming, and it's about this uniform continuity. And I know this can be confusing, and this example here strikes at that point that for some functions, you can find this delta to be independent of the value C. And in that case, it doesn't matter when we talk about what point to be continuous at. It's going to have this uniform property, and it's called uniform continuity, and it's coming. I forget when it's coming. Forget when it's coming. So maybe over in 129. Maybe this is the next time it's coming. So you can see there's a word like uniform continuity out there. And then there's a result over here about compactness. So this is something that we're going to be proving at some point. It's coming over in section 4.4. And so the meaning of that is when we work to get this delta, it might be that we have lots of different choices of delta. And if we just have one choice that doesn't depend upon what point we're studying, well, then we're going to get this uniform property. And being uniformly continuous is just somehow, it's a much stronger property than just being continuous. All right, are there any questions about these first couple of slides? Okay, then we're going to push forward a little bit. How does one check continuity? Just like when we had compactness, like we want some easy conditions to check. So how does one check for it? Well, there's a little lemma. There's a little lemma that says that f is continuous. I'm going to start writing cont for continuous at a point if and only if, and then we put in something that is more operational. And the way we're going to do it is you take any sequence inside the domain. For any sequence inside the domain that converges to C, we have that the function values deconverge as well. So you can characterize continuity simply by taking sequences that converge, and it has to be true for any one of them. We're going to do an example in just a second. Let me try to sketch out the proof, like what are the steps in here that would make this work. Well, we could move down, right? It's an equivalence. So we have to prove two directions. So we're proving it down. If I take a sequence, let xn go to C, and then I want to prove this property. So what is that property? I need to take an epsilon. So we're going to let xn, we're going to let epsilon be arbitrary. Right, so I need to prove this property, and the thing that I have at my disposal is continuity. So because f is continuous, right, I can find this delta such that if I squeeze x close to C, so x is any number inside A, such that when I squeeze them close to C, so if I keep them less than delta, then that's going to imply that the function values stay close together. Right, so for any x that has this property, such that for any x in A, such that this difference is small, I'm going to have that the function values are less than this epsilon. Okay, but then we're in business because I let xn go to C. So because xn goes to C, right, what does that mean? There exists some number such that for any numbers that are even bigger, I will have that the distance between xn and C is less than delta. So my xn sits in here. So it's because xn dissatisfy this property, well, then given that it's continuous, I'm going to get the other one, right? So this implies that f of xn minus f of c is less than epsilon for any n bigger than n. Okay, but that's what it means to converge. So this was one direction. The other direction is the other direction, the way that Abbott does it, it's a little bit cumbersome, but let me try to write it out what Abbott does. So he says we should argue by contradiction. We should argue by contradiction. Right, so we're assuming now, assuming the bottom part, we're assuming we have this property for any sequence, and then we're going to negate what we have over here. So we're going to negate what it means to be continuous at a point C, right? So argue by contradiction. So we're going to assume that this thing here is false. So that means that there is some epsilon. There is some epsilon such that for any delta, we can find an x in the domain such that x is close to C, but the image values are not close. So argue by contradiction, let us assume that this is true. And now we want to get a contradiction. We want to get a contradiction with the property that we have here. And how are we going to do that? So let's let us construct. Well, what do we have? We need to construct these x's. So let's construct xn that converges to C as follows. Using here, so this is gonna work for all delta. Okay, so I'm gonna use delta to be 1 over n. Then what do we say here? Then I can find these xn's such that xn minus C is bounded by 1 over n in distance. But when I look over here, the absolute value of f of xn and f of C, this is still big. Right, so the first part, this part here, this is the thing, this gives us that xn converges to C. And this part here, this gives us that this gives us that the xn's, the f of xn's, they do not converge. This here means that f of xn does not converge to f of c. But that's a contradiction because this was to be true for any sequence that converges to C. We should have it this also works. So this is the way that Abbott does it. And I know this can be you're looking at this and it can seem pretty dry and like what on earth is going on, this epsilon delta. I wanted to show you a quote. It's a quote here in this. I think I showed you this. This is the standard topology book that is being used across the US. This is a Moncrief's book. And let me just show you what he calls this epsilon delta definition. So it's not something I'm making up. This is in a standard reference. And here's what he writes. So he's writing, in analysis, one defines continuity of F via the epsilon delta definition. And then he calls it a boogaboo over the years for every student of mathematics. Right. So this is his take on what this epsilon delta definition should be called, and this is what we're seeing. Right, there's a lot of symbols, and it can be hard to internalize. So I'm gonna try to see if I can get a few points across using examples and using equivalent definitions. But there's no way around this epsilon delta definition. This is what our textbook uses, so we need to do it too. But the first thing to get across is to revisit an example that we have had a lot of fun with when we did connected sets. So let me try to do an example. If I give you this example that we've had with sine 1 over x when x is positive, and then we put in a 0 here. This is when x is 0. This should be familiar to all of you. We've had here a number of times, and here it goes again. So we could ask, is this thing here continuous? So is f continuous? What do you guys think? But the normal well, you go try to make a picture of it. I mean, we've done this picture here before, so but let me do it again. You go to Mathematica, say, and what you're interested in is you want to look at a function that is sine 1 over x, epsilon from say 0 to 1, and you look at this picture. Then does that look like a continuous function? What do you guys think? Where is the potential problem? What value of x is the potential problem? At 0. Very good. So I talked to some of you about like how to read a problem, right? And it's almost independent. Like whatever I would write here, as soon as you see what the domain is, this is where the problem is. Like it's at 0. It's not going to be out at 5 or 7. It's going to be around 0, right? So if we want to, so do we want to have it to be continuous? So let's check out the point. Do we have that f of xn, if I take the limit as n goes to infinity, do we have that we always get the same? Do we have this no matter what? No matter what sequences xn and yn that converge to 0. And this was the property that we were continuous at a point. So here the point is 0, as you guys pointed out. This is the one that's the troublemaker. And that means that you take any sequences that converge to 0, then you need to have this property. And do we have that? What do you guys think? Fernando, he says no. Then Fernando, I would like to see, can you give me 2 sequences? Can you give me 2 sequences that converge to 0 such that these 2 things are different? Well, this is back to your homework. I think you had them in your homework at some point. If you take like 1 over, what was it, n times 2 pi, and you do the other one, it's like 1 divided by n times 2 pi, and then you have to off-kilt it a little bit, like with pi over 2, I think. But these things deconverge to 0, right? This one here goes to 0, n explodes up to plus infinity. This is going to go to 0, and this is going to go to 0. But what happens? What happens if I look at sine of 1 over xn? Well, this is going to be sine of n times 2 pi. What is that equal to? And what happens if I look at sine 1 over yn? This is going to be sine then n 2 pi plus pi over 2. What does the first one equal? The first one is a 0. The second one is, this is the one I always mess up. So this is a 1. Right, so when I take the limit of a bunch of zeros, I'm going to get 0. I take the limits of a bunch of 1s, I'm going to get 1. These are not the same, but then it's not continuous. And Fernando was right. This is not true. So it's important here that this is this for all, right? We should keep that in mind, right? This here is for all. Let's tweak the example a little bit. This example, as you will have realized at this point that this must be an important example because it's been in the course more or less on a weekly basis. And we're not even there yet. There are more applications of these examples that are coming up. We're going to move into taking derivatives of functions soon, and there's no end to what you can do with this example and derivatives. But let me just give you a little variation of it. So let's do another example. We do a little variation. We call this, before it was F, let me call this one to G. And so now what happens is we take X outside here, and then we do sine. And this is going to work when X is positive. And we're going to have a 0 here. This is going to work when X is 0. Right? So again, without writing anything, the troublemaker is going to be, the potential troublemaker is going to be X equal to 0. Now we have this. Is he continuous? Well, let's take a sequence. So Priya is saying yes. So Priya, what is it? What is the feature that makes all this stuff here work? The X is the key, right? So X goes to 0. And what is the other feature? What about this sine 1 over X? Right, sine over 1 over X is the bad guy. But what kind of a property does this sine over X have? Fernando's right, this is bounded. Very good, right? So now we just put it together. We want to look at G of xn, right? So we're going to take an arbitrary sequence, let xn go to 0, then G of xn, well, minus G of 0, right? How does he operate? This was a 0, so this is just the absolute value of X sine 1 over X. But this is bounded by absolute value of X. Xn, sorry, it needs n, see? Right, and this goes to 0. Later on in the course, we're going to be having fun with this example here, because it has, if you tweak it more, you're going to get crazy things about derivatives. So let me just show you how, when we get into chapter 5, maybe next week or a few weeks from now, I don't know how far we're going to get. You're going to get more of this nonsense, right? So now we have X here, and you have sine 1 over X. And now we start taking derivatives. And when you take derivatives, you're going to end up in this crazy situation. In particular, it's the one with the square, right? So we did X, so here we have an X square, and you're looking at this thing here, and you start taking derivative of this thing. You get this example out of it that you have a function that has a derivative, but the derivative is not continuous. So it's like an example of a smooth function that has a derivative, but the derivative is not continuous by itself. And you can get that out from this example here. It's the oscillation of this sine 1 over X, and then you dampen it. Here we dampen it by X, as as Priya pointed out, but you can also dampen it with X squared and so on. So we're going to return to this example here in the not so far distant future. Any questions on these examples? Results here so far? Does it all make sense? So as we saw in the topology book, right, this was this, he didn't use the word nonsense, right? But so what is a definition of continuity that is less confusing? I had written it on the board, and I want to spend some time here today going over this this other way of viewing continuity, right? Because I had made this point before that so the open sets. So whatever notion, so our notion of open sets control everything, right? It controls compactness, it controls connectedness, and it controls continuity. Some time ago, one of you asked, so is it true that if I change the notion of being open, then I'm going to change all these features here? And I said, yes, it is. And when I was preparing today's lecture, I said, maybe it's time to make promise on this. So I want to try to highlight this even more, that it's really the open sets that control everything. In particular, today's lecture is about continuity. I want to show you how continuity is related to open sets. And when you look at this epsilon delta definition that we've seen here, the reason that Moncrief doesn't like it is because this is not the appropriate definition of being continuous. It works really well here in R and in Rn, but in general, it is simply not the right way of doing it. So what is the right way of doing it? And this right way of doing it, this uses these open sets like directly. So let me try to show you how it's done. So this here is the topology definition. And Abbott, he hides this. This is Abbott's exercise 4.4.11. So the topology definition it is much cleaner than this epsilon delta that we did. The topology definition is that if I take a function, so I'm going to start with the domain being R, because this is what Abbott does in his exercise. This is continuous if the pullback, so for any open set in R, so we can put D's and M's here. This is okay. This definition here works in full generality. This is for any open set. O open. The pullback is open in R, right? So if you would have, maybe you should put a D here and M here. Right? So you take something that is open over in Rm, and you look at the pullback, and this is going to be open in Rd. That's the definition that works in full generality. Right, so so just to see the connection, just to see a connection, to see that this definition implies what we had before. Implies our earlier definition. Let's take D and M just to be one, and then let's take, for this definition here, it actually suffices. So here it actually suffices to take O's to be these neighborhoods. So V epsilon, V of I don't know. Let's call it epsilon. Just open intervals of points C for C and RM and epsilon positive. And so just look at pullbacks of these open balls. So here I use the word implies, so it is really equivalent. But let me just do the implication, since we're trying to have a more informal discussion about this. And so how would one go about doing this? This is the definition we're working with now. We want to show that that implies the definition that we had before. Right? So let's take a point. Let's take a point over in the domain. So this is going to be, in this case, it's going to be an R. Right? Let's take an epsilon bigger than 0. And then if I look at the interval f of c, right, so that's going to be something over in the codomain. I subtract a little bit and I add a little bit. But this is going to give me, this one here is open. This is an open interval in the codomain. This is an open interval over here in the codomain. So then we use the definition. So because f is continuous, the pullback, this is open of that particular set. So let me write out what this pullback here is. We've had it a few times. These are those x's in R. Well, it's going to be in RD, but we have D equal to 1. So it's those x's in R. So when I plug them into F, I get something inside O. Right, and of course, O has a very specific form. So I can write this here as those x's such that f of x belongs to the interval f of c minus epsilon, f of c plus epsilon. And so there's no doubt, in particular, if I look at the value f of c, right, that's going to be scooched in between here, right? So c is here. But now we know that this is an open set. Because it's open, because f minus 1 of O is open, I can find a ball that exists at delta such that the ball around the point, this is inside f minus 1 of O. But what is the ball? And the ball is, well, it'll be C minus delta to C plus delta. That's how our open balls look like in R. So now what do we have? Well, if I let x be close to C, in the sense that this is less than delta, then what? Well, then x is going to belong to the ball. Right, so this here implies that x belongs to the ball, right? Because those are the points that are within delta from C, and so x has this point. So x belongs to that ball, v delta of C. But then I'm inside the bigger one, so x belongs to f minus 1. But what does that mean? Well, that means that the equality here is true. But this here means that f of c minus epsilon is less than f of x is less than f of c plus epsilon. And then we're done, right? This means that by keeping the values in the domain close, I'm going to have that the values in the codomain are close. F of x is going to be close to f of c, right? It's going to be within epsilon range. So this definition here, it does not use epsilon and deltas. It just says that pullbacks of open sets are again going to be open. Are there any questions on this part? So there's one little problem here. The problem is that we wrote f of rd here. And so Abbott, so I want to show you this. And Abbott, he considers f of a going into R for some subset. So A here can be any subset. So it would be natural to say that, well, if you try to apply this, so it doesn't work. It doesn't work to demand. It doesn't work to demand that that f minus 1 of O is open for all O inside R open when A is not R. And let me try to, so Abbott has a point that his definition appears to be more general because he can allow this arbitrary set A there. And what we had done here was going from R, and just to hammer it home, like when you look at this exercise 4.4.11, if you look at this exercise 4.4.11, again, he has a function that is defined on all of R, right? And then he's looking at these pullbacks, and then if and only if you're open whenever you have an open set, and so on. So that's fine, but just look out for the domain here, right? This here is his domain in this exercise. Whereas when he defined continuity, over here, right, then he had a set A. So there seems to be a lack between the two. This one here is more general. And okay, so how does one rectify that? Why does this not work? Well, for example, this might be a little silly example, but no, nonetheless, it does show. If I were to use this definition here, right, and I'll take f of x just to be x, and I'll take A to be the interval 0 to 1. But then if I were to say that that this should be the property, you can see it would fail because the inverse of, say, R, this would be exactly A, right? This one here, this is open. This one here is not open, right? So if I were to do this one here, it would fail. This function here would not be continuous. So this is not the right definition to have when you're dealing with a subset of R. And so what to do then? So we need what's called the subspace. So yeah, the subspace topology. So you take a set in RD, then we say U is open in A if U is open in A if U can be written of the form A, and then you need to intersect here with O, where O is open. And now it's a good one. So now we can have the definition. The definition now is that a function that goes from A into, say, Rm, this is continuous if minus 1 of O is open in the subspace topology. In the subspace topology, for all O which is over in the image, that are open. And you can see how it fixes up the problem. It fixes up exactly this example's problem here. That if I looked at this example, if we go from 0 to 1 into R, f of x would just be x. Then what? Then the image, the pullback of R, the pre-image of R, this was the interval 0 to 1. But that is open. This is open in the subspace topology. Because what? Well, it has to have this form. So 0 to 1, this is indeed equal to, well, 0 to 1 intersection with something open. So for example, -2 to 2. Long time ago, in the very beginning, I think it was Fernando that asked me in the lecture, who said that the open sets in the usual topology that are both open and closed, are those the only ones, the empty set and R? And the answer to that question is yes. And so what we're doing here is, in this subspace topology, we're removing that property onto A. We want to have that even though A is closed in the usual sense, in this subspace topology, it's actually open. And it's the same property that R has in the usual topology on R. So this is the right definition for continuity if you're dealing with continuous functions that are defined only on a smaller set, and we often have that, right? Just looking back at the examples that we had here, these functions here, they're not defined on R, right? They're defined on the positive line, right? So A here is the interval from 0 to infinity closed at 0. So we need to have a notion for continuity on such subsets. And if one wants to do this topology definition, then you have to work, then the right notion to use is this subspace topology, which is not bad, right? It's just you take the set, and then you just intersect with open sets coming from the bigger space. I won't say any Priya, that's too much. The correct phrase is, so a closed set can be open in the subspace topology. That's correct. Like this one here is closed in the usual topology on R, and it is it's also open in the subspace topology. So I don't like the word any. If you could just write a closed set, then I would be happy. Are there other questions? Yeah. Yeah, I mean, that's not hard, right? If you take this one here, if I would take the interval from 1/3 to 2/3, I don't know how to write this as A intersection with O, right? This is equal to 0 to 1 intersection with O. This one here is open in R. Right, this is a closed set, but it's not open. But this is inside 0, 1, but it's closed. This one here, this is closed in R, and is also not open in the subspace topology. Aha, okay, so now you're talking. I like that. Okay, so let's change the premises a little bit. So excellent question. Excellent question. And if you're looking at, so let me just so Priya is asking tough questions here, and I really like it. I appreciate it very much. Let me just bring up here the homework. See, this is your homework that is due next week. Priya's question is about openness. What happens if it's open? And you can see here in this homework, there is the word open. It's right there. And it's this O here is always open in this problem. And what Priya is striking at is, why on earth do I keep saying this stuff here is open? Well, let me show you why I'm keep saying this stuff here is open. What about this openness? So so let's do an example. If I take A is open in RD. Well, then U open. Then U open in the subspace topology implies that U is open in RD. And it's not hard to see why, right? Because you write the property that you have this, right? That says that U has the form U is equal to A union O, right? For some open set O in RD. Right, now we take an intersection of two open sets, right? So now we use that this is open, right? So this part here, this is an intersection of two open sets. This is again open. Right, so if the set that you start out with, if the domain of your function is open, so this here could be, right, this one here, this could be like 0 to infinity. It could, for example, be 0 to infinity. Then the open sets in the subspace topology are also going to be the open sets in the topology that we use. Excellent question. More questions? More questions? The last part I want to do is this is a bit beyond it's a bit beyond what we would do in a class like this normally, but I really do think that it's like this open sets control everything. I really think this point we have to get it across, and I think it was Aya who raised the point, like, so what happens if I switch the topology on R around, right? So what happens if I change the topology on R? We're not talking about subspace topology. What happens if I change it? We've been working with the standard topology on R. So we've been working, right? So we have worked with, and this is exclusively with the standard topology on R, right? So what does it mean? O is open if for any point in there, there exists some neighborhood around it that is inside the set. And so one could ask, like, what happens? So we work with the standard topology. So what about non-standard topologies? So I brought up, here are a bunch of topologies. There are 5 of them. Consider the following topologies on R. So there's the standard one, that's the one we're good at. But then there are like 4 others. And so this is just to give you an impression that there's a choice to be made here. When I change the topology, I'm going to change all the compact sets. I'm going to change all the connected sets. I'm going to change all the continuous functions to be something else. When I switch around the topology, I'm going to change the foundation of what we're doing, and therefore all the results that we've seen are dear subject to changes. And so, for example, we're used to, in the standard topology, that compactness is equivalent to being closed and bounded. Just today, we did another result, which is something that one can grow quite familiar with, namely to check for continuity. To check for continuity, let me just show you where it is we check for continuity. Today, when we check for continuity, we had this equivalence. You are continuous if and only if I can test for continuity using sequences. And so this is somewhat of an analog to like an easy way of testing if a function is continuous. And it's hard to see from this theorem here that where are the open sets? Just as when we tested for like compactness, like where are the closed and like how do we get from these closed and boundedness to saying that we can thin out an arbitrary open cover? This is not obvious from a result like this one. So I thought we should spend we have like 15 minutes left. Let me try to go a little bit beyond and try to dig into one of these non-standard topologies and just see how crazy stuff can get. So we go a bit beyond. So let's try a non-standard. A non-standard topology. Right. So this here is, for those of you that are worried about stuff going on the test and on the homework, like this here is beyond what I would demand for you guys to feel comfortable doing. But I do think that since the issue has come up, we should have some appreciation for the role that open sets plays. So I'm going to change it around. So the non-standard topology that I'm going to be looking at is what is called co-countable. A co-countable topology on R. Okay, so how is this defined? We're going to say that here we say that A is closed. We're going to say that A is closed if A is equal to R or A is countable. And countable here, this includes finite sets and the empty set. So this is we're going to say that a set is closed if this is true. Right now, of course, we're going to say then that O is open if the complement is closed. So this is kind of a crazy topology. Now we're changing around what it means to be open, what does it mean to be closed. Now we're using this, we're saying that a set is closed if it's either equal to the entire set or it's countable. And why does it work? So this is a topology this is indeed a topology. But there are a few things we have to test. For example, we have to test that arbitrary unions of open sets will again be open. Okay, so we can test arbitrary closed sets. If I'm closed and I take an arbitrary intersection, okay, so is it countable? Will I take arbitrary intersections? This is countable. This is countable whenever AI is countable. And likewise, if we take unions, but now we only have to do finite unions of closed sets. So we do a finite union, say up to I of AI. Take a finite union of countable sets. Well, I'm going to be countable. So these were properties that closed sets should have. Equivalent, you can look at the complements and get the open sets. And then you need these Morgan laws, De Morgan laws that you guys have worked with in the homework as well. This stuff here works. It qualifies as a topology. It is far away from anything. This is not the standard one, or this is a different one. We're saying that something is closed if it's countable. It does form a topology. And now we can start looking at examples in this topology, right? We can start talking about what kind of sets are compact, what kind of functions are compact with this topology. Right, so we consider continuity. So consider a function that goes from R into R. Right, so over here, we're going to put the standard topology. And over in the domain, we're going to put this crazy beast we call the co-countable topology. And the function I'm going to be looking at is very simple. This is f of x. This is just x. So we would hang our hat on that this thing here, this is a continuous function. This is a continuous function. But that's not the case. That is not the case, because if I looked at f inverse, right? So it's if it is to be continuous, right? I should be able to pull back open sets and get open sets. So if you looked at the inverse of the interval 0 to 1, this here, this is closed in the standard topology. And what kind of points would I get? That this would be exactly 0 to 1, but this is not closed. This is not closed in the co-countable topology, right? Because it's not countable, right? So f here is not continuous. So f is not continuous, despite it being just f of x equal to x. So this is one example of, if I change the topology to something else, basic properties that we're used to, like the function f of x being continuous, and this doesn't hold anymore. And the same thing is true with all these other properties. And the one I want to hone in on here is this one. Like we had this equivalence characterization between continuity in the standard topology and this sequence representation. Right, so now we have a function here that is not continuous. So what about if xn converges to x, then f of xn converges to f of x, even though f is not continuous. Even though f is not continuous, And so this property that we had here, namely that continuity, is equivalent to this property. And that apparently fails if I change around what I mean by open sets. So here I can have that sequences converge and the function evaluated these arbitrary sequences deconverge, but the function I'm looking at is not continuous. And one reason why I wanted to go through this example here is because I have seen some of you. So in the standard topology, what does it mean to converge here? In the standard topology, right, we can have the 1 over n. 1 over n converges to 0, even though 1 over n is never 0. Right, this is a property that we're used to, and this implication here, this is underneath the hood here. We're using open sets to describe this sort of convergence, and we've been used to this in the standard topology. So that doesn't work if in the co-countable topology this is not true. We have we'll have that xn converges to x if and only if there exists some number such that any number later you'll have that xn is exactly x. So in this co-countable topology, these sequences, they eventually become equal to x. This is, of course, not true in the standard topology we have. And I've seen some of you, even in your midterms, there seems to be some confusion about this point here, right? When we're talking about convergent, we're not requiring in any possible way that the sequence we're looking at should be equal to this limiting point. Just as we're not requiring, if I take the supremum over this sequence here, or the infimum over this sequence here, we're not requiring that we should be able to find a number such that when I take that number and I plug it into this 1 over n, that I would get exactly the infimum or the supremum. And the infimum here is going to be equal to 0, but there is no n such that 1 over n is equal to 0. What it means is that I can get arbitrarily close to it. And this is what does it mean to get arbitrarily close to it? Well, this is what this topology does. It tells us how to get arbitrarily close to it. Right, so what does it mean for xn to converge to x? Well, xn converges to x if what? If I take any open set, for any open set, if for any open set, x is in the open set, we will have that there is a number. There's a number such that for any later indices, we'll have that these xn's are also in that open set. Right, and then you can put in here whatever you want. You can put in the open sets that are coming from the standard topology. You can put in the open sets that are coming from this co-countable topology. Right, so if we do this here for the co-countable topology, then we're going to get the property down here. Let me just show you that. So claim, so xn converges to x in the co-countable topology if xn is equal to x eventually. Right, so there is an n such that after that point, xn is exactly equal to x. And it's not difficult to see the proof. What you do is you say, let me take a set. Those are those xn's for which xn is not x. And this is a countable set, right? Because the xn's, they run through the natural numbers. So this is a countable set, so it's closed. that was the definition of this co-countability, right? A set is closed if it's countable. Okay, so then if this one here is closed, then O being the complement, this is going to be open. Then we use the definition. Then we're going to use the definition. We're going to have that. So if xn goes to x, there exists an n such that when I'm later than that n, what will happen is that my xn belongs to O, belongs to O is equal to AC. So if what does it mean to belong to the complement? It means that I'm equal to, right? So for any n that are sufficiently big, we'll have that xn belongs to the complement, and that means that it's equal to x. So it's a crazy topology. It means that you converge if and only if you're eventually constant. And so now we have the property that if I look at f of xn, by the definition, this is xn. Okay, this is equal to x for any n sufficiently big, but this is equal to f of x. So we have this property that the function, this identity function, it's not continuous, but it has the property that if I just look at the function values it has along convergent sequences, I have the property. It's just so a result like the ones that we just proved in class, a result like this one here, this is not true if I change around what the open sets are. And therefore, one should be that this is something to be mindful of, something to be a little bit careful about. If you change around what the open sets are, all these results that we have proven and using in the homework and on the exams and so on, well, they may or may not be true anymore. And here's a specific example of a highly non-standard topology put on R, this co-countable topology. This is far away from the topology that we're used to working with, but it is nonetheless a topology. So we can talk about continuity, we can talk about compactness, we can talk about being closed in this topology and so on. And one feature that the topology has is that if you talk about convergent sequences, well, eventually they're constant. And this is also a property that the standard topology does not have. Okay. This was a little bit of a reply. So is X in the co-countable topology a limit point? So what was the definition of a limit point? So just bear in mind here, we need to be careful because when you're talking about a limit point, we had these, the way that we defined a limit point would be to say X is a limit point for A if what if I would take a little neighborhood here, and then I would intersect with A, and I wouldn't get 0. Right, and these ones here, these were the open balls. These were the open balls. The epsilon of x would be those y's such that the distance between x and y was less than epsilon. And for the, I don't know, for the co-countable topology, we need different balls. The proper word here is this is a sub-basis. And I'm not even sure there is a sub-basis for the co-countable topology. So without this notion here, I'm not sure how to define the limit point. You can see we had proven something like that this here was equivalent. We had proven a result that said that this thing here was equivalent to saying that I can find a sequence inside A. Xn is not X, Xn is not X. such that xn converges to x. We have proven a result of this one. And stuff like this here relies again on open balls. If I change around what I have here, I am not sure you get such a property here. So what is the description of limit points for the co-countable topology? I am not sure. Right, so there are lots of these non-standard topologies that you can put up, and they all I mean, you can see they're obscure because they're not standard. But an example like this one, it really does highlight that. Really does highlight that these open sets here, they are, yeah, I mean, they control everything. So if I change the notion of open sets, well, I'm going to change around the entire foundation of what we've been doing. And sometimes you need to do that, right? Depending on the problem you have at hand. There might be leeway in choosing the topology that you're working with. Here, the difference between the standard topology and the co-countable topology is huge. It's like night and day. You can find other topologies that are different, but you're not like that different. Here, it's a huge difference. I mean, being close, this is something that is countable. This is pretty extreme. Yep. Are there other questions? So again, I just included this last one here. Like a little appetizer to see that, well, I mean, that the open sets are really important for what we're doing, even though if you push to the background, if I start changing them around, like this result here, which is a result that you'll be using lots of times, we'll be doing a lot, we already have, and we'll keep doing this. Like when you guys recognize the, when you guys were doing the example with sine 1 over n, this was already something that we had done in class. We already taking these limits here. So if I change it around, this won't work anymore. Alrighty, we are out of time. Are there any more questions? Otherwise, I'll see you guys on Wednesday.
Professor, a little bit more about this. Like one of the definition of open sets is that it has its limit point outside of the set, right?
Yeah, I mean,
but we can't use that one for like to kind of get to another topology, or we can't define or modify the definition with like this specific definition of an open set, right?
But so you can see why stuff like this might it might simply just not just if you're saying like, well, I have the interval 0 to 1, right? I want to look at the closure. I want to say that the closure is equal to the set, a union, and then well, in this case it's 0, right? And I want to write this 0 as a limit of something that comes from in here, like 1 over n. But you can kind of see that this here is for the standard topology. If I did it for this co-countable, if I would take something like 1 over n, this is still, of course, inside here, but that does not converge to 0 in the co-countable topology, right? Because this is not eventually constant.
Yeah.
Right. So then, I mean, I am not allowed to write a limit of 1 over n in this co-countable topology because this does not exist.
Okay.
Right. So then I'm gonna have a problem up here. I mean, how am I gonna do this in this one here? How am I gonna write 0 to 1's closure? If I'm not mistaken, I actually think the closure is exactly this.
Okay, yeah, I see.
I'm not. This is my guess. This is my guess. You're gonna get, yeah. That would be. I think this is what you're going to get in this crazy topology here. You're not going to get this closure that you're used to up here in the standard one. And the reason that this stuff is falling apart is because I can't do this. That limit does not exist in this co-countable topology because it's not eventually constant.
Mm-hmm.
But okay. This one here, take this with a grain of salt. I haven't thought about that before now, but this is my gut feeling that I think you're going to get this.
Yeah, I just couldn't see where it breaks down.
Yeah.
Okay.
I mean, lots of these things that you take for given, because you've been taught this for years, right? And we've been taught it in this class all the way up. It's like the 1/n converted to 0, right? You will tell that to anybody and you'll agree. But the problem with it is that if I change the meaning of what does it mean to converge and start phrasing it in terms of these open sets, which is the appropriate way of doing it. Right? That is, I mean, the right way to phrase stuff is in terms of open sets. And if I start changing around what these open sets are, then this is not necessarily convergent anymore.
Mm-hmm.
If I pick something that is sufficiently crazy, right?
Mm-hmm.
It has to be something that's sufficiently crazy because I'm trying to illustrate a point, right? So if I could choose another topology that would have like more subtle differences, but then it wouldn't be as outrageous and it wouldn't have this shock effect that I'm trying to get at here.
Mm-hmm.
Okay.
All right. Thanks so much.
You're welcome.